All right. So I wanted to come to this part. We're not going to do this proof, okay, but I just wanted to at least highlight, okay, the slope criteria for parallel lines. You already know this to be so, okay, but we're going to state it here. Two non-vertical lines are parallel if and only if they have the same slope. Okay? So very straightforward stuff there, nothing new, nothing mind-blowing. All right, let's turn the page though, and I think we'll skip that on to page 497. Okay? So, on page 497, you're going to get an idea of the kind of expectations for, or how we're going to be using, we're going to be doing this unit. Okay. So, we can use the slope criteria for parallel lines to analyze figures in the coordinate plane. All right. So, example 1 asks us to show that each figure is the given type of quadrilateral. Okay. So, for letter A, we're asked to show that ABCD is a trapezoid. Okay. So, this quadrilateral here, we're meant to show that this shape is a trapezoid. Okay. What makes a trapezoid a trapezoid? What makes a trapezoid a trapezoid? How do we know if a shape is a trapezoid? Or if a shape is a trapezoid, what do we know about it? So Eli?
Well, there has to be at least one pair of parallel sides.
One pair of parallel sides. Right, exactly right. Okay? So if we, that's like the definition of a trapezoid, at least one pair of parallel sides, right? So looking at our picture here, okay, and this is not all of the work, but you can at least like this kind of like preparation, right? We look at this and we say, does it look like this shape maybe has one pair of parallel sides? It does, right? Okay, what sides look like they're going to be parallel here? A, B, and DC. It looks like, okay, they are going to be parallel. Since we're in the coordinate plane, how can we show for sure that A, B, and DC are parallel? What do we want to compare? They're what? They're slopes. Exactly right, okay? We just got done talking about on that very, very first page, right? Two non-vertical lines are parallel if and only if they have the same slope. So let's just find the slopes of A, B, and DC and see if we get the same number. Okay, now the book has you actually like calculating the slopes using the slope formula, so feel free to use that if you want to, rise over run, y2 minus y1 over x2 minus x1 for these. But do we need to actually do this, or what could we just do? Just count. So from A to B, we're going to rise 2 and run 3. So I'm going to use the slope of AB. Okay, is literally just up 2 over 3. Right? And then DC, we can do the same thing. We can do rise 1, 2, 3, 4, and run 1, 2, 3, 4, 5, 6. So the slope of DC is 4 over 6. Now, when we count them, right, we have slightly different numbers, but we know 4, 6 can simplify to 2/3, right? And so therefore, since AB is parallel to DC, then ABCD is a trapezoid. Okay? That's the idea. That's it. Okay? So you can see why we were emphasizing those properties so much, right? Is that when we get to a point like this, right, we want to be able to show what it takes to be a trapezoid here. We just want to show the slopes are parallel. Okay? Thank you, Grace. All right, let's take a look at the next one here. Letter B. Show that PQRS is a parallelogram. All right. So what are some options here that we have to show that this is a parallelogram? What's one thing we can do? What makes a parallelogram a parallelogram? That's one option here. Luke? Okay, so we can show that each pair of opposite sides are parallel to each other. Okay? What else can we show here? Yeah, Avery?
One pair is parallel and congruent.
Aha. So how will we show that any of these things are congruent? What would we need to use here since we're in the coordinate plane?
Well, when you're counting the slope, it would be like, first you figure out what the slope is, but when you're talking about the rise over run, it's like they both have to be the same. Like one can be 2/3 and then one can be 4/6.
Okay, so that's true. That's true. You could use that here. What if we wanted to, but that wouldn't give us the actual length, right? How can we find the actual, for example, let's just say we wanted to show that PS and QR were both parallel and congruent. How can I get the exact distance here from P to S? Yeah, distance formula. I guess I gave it away with what I said there. So, but yes, exactly right, Preston. Distance formula, okay? Yeah, so we can also use distance formula here, okay? I know that sometimes you end up with like square roots and stuff like that, but remember, if the square root of, if this thing is like the square root of, actually, let's see, I guess what would it be? 4 and 1, 2, 3, 4, so that's 16. So it would be the square root of 20 would be this length. If you see that this is also the square root of 20, you're good to go. Now, Avery's not wrong with what she was saying there. She said that if you count the slope, so down 1, 2, 3, 4, over 1, 2, so down 4, right 2, if you get that exact same count for Q to R, that means it is going to be parallel and congruent. So that's another option there too. All right. Let's do, I think it looks like in the book here they want us to do what Jackson suggested, where we have the opposite sides are parallel, right? That was you, Jackson, that said that, right? No, who said that? Luke. I'm sorry, Luke. I don't know why. Yeah, yes, Luke. I want to give credit where credit's due there. So yes, the slope. So let's do here the slope. And again, let's just count it. We don't need to actually do the slope formula. Of course, if you wanted to, you could use the slope formula there, right? Or if you didn't have the graph, you could use the slope formula. But since we've got it here, let's just go ahead and count. So down 2 and right 1, 2, 3, 4. So negative 2 over 4. Okay. And I'll go ahead and do the slope of SR. Okay. Slope of SR, so down 2 and right 4 as well. So that means both of these slopes we can simplify to what? Negative 1 over 2. It's not necessary to do that. You can keep them this way if you want, because you can see that they're exactly the same. But it is helpful to know that we can simplify them, right? All right, and then last, let's do the slope of PS, which would be down 4, right 2, so negative 4 over 2. And then the slope of QR, also down 4, right 2. Which would be negative 2 over 1, negative 2 over 1. Okay. Are these slopes perpendicular? Are these perpendicular slopes here? No? But they're like flipped though, right? They're reciprocals, yeah. So does that mean they're perpendicular? I hear yes, I hear no. All right, so what is it then? So Avery, you want to explain? What do you say?
They're not opposites.
They're not opposites, right? So they are reciprocals, they're not opposites, right? We can also kind of visually confirm this here, because if, for example, if SR was perpendicular to PS, so if SR was perpendicular to PS here, what kind of angle will we see right here? 90, right? And you can see, again, assuming this is drawn to scale, and I think it is, right? It's on the coordinate plane here, graphed appropriately. I think it is, again, on the coordinate plane here. Yeah, we don't see that 90-degree angle there. So not quite perpendicular, right? Opposite reciprocal. Not just reciprocal, it could be opposite reciprocal too. Okay? So, yep, there it is. Okay, so since PQ is parallel to SR and PS is parallel to QR, then PQRS is a parallelogram. Okay. Mr. Wood, do we have to write that sentence out at the end? Yeah, you really should, okay? Because don't leave me to conclude what you're showing here. Yes, you need to show the calculations here, okay, that support what you're going to say, and then in your statement, analyze what your calculations show, and then what that then says about the quadrilateral. It is a parallelogram. Okay? Questions on? Be there. All right. Let's go to the tries here. Okay, so go ahead on the next page. Okay. Go to the next page. Okay, and you can use whatever methods you want to determine whether this is a trapezoid or whether this is a parallelogram. Okay? So it's up to you. So go ahead and try 4 and 5. Show that they are trapezoids and parallelograms, and I'll do the same thing. I feel like one more minute here. One more minute. I see some people still working. So one more minute. Okay, so again, no surprises here, right? It's kind of just like what we did. Okay. Number 4, got the slopes, right? We have LM parallel to JK, so JK is trapezoid. Number 5, I got the slopes, and so I said AB is parallel to DC and AD is parallel to BC. And so therefore ABCD is a parallelogram. I also went ahead though and calculated the distances for AB, DC, AD, and BC. So again, this is not the only strategy you have to use here. Is it probably the most efficient, the quickest? I'd say so, right? It's much easier to just count the slope, right, than it is to use, distance formula or Pythagorean theorem to help us figure out, AB and DC or AD and BC here. But you can see in the work, right, AB's length is the square root of 52, DC's length is the square root of 52. Those are the same. So opposite sides are congruent. And then AD and BC, those are both the square root of 5, so another pair of opposite sides are congruent. So we could have said that this thing's a parallelogram because opposite sides are congruent. We also could have said because, as Avery said earlier, we have one pair of sides that are both congruent, right? AD and BC are equal, and also parallel because the slopes are the same. Okay. Likewise, here we could have said the same thing. AB and DC are parallel, and then their lengths are the same. So, okay, at least 3 ways to answer this one. This one, it's really you have to say, JK and LM here are the same. Okay. Do we have a way to come up with the angles here? So like angle D, angle B, angle A, angle C. Do we have a way, using the coordinate plane, to help us come up with angles here? D, B, or A and C? Do we have a way to come up with the angles there so we could maybe use opposite angles are congruent? Do we have a way to do that?
Sort of.
Sort of?
The only way I can think of is calculating the slopes for both sides, all the sides, and then figuring out the. But I mean, that's just a lot more work.
Yeah. I just don't know if you come up, but I don't think we could come up with the actual degree measures here.
Yeah.
I don't think that is possible. Not with what we know, at least. I think later with law of sines we could figure it out. But then yes, it would be a lot more work and not really worthwhile, I would say at that point, right? Who wants to do more work than they need to, right? Not me. And yet, I assign you guys work all the time. Anyway, hypocrites, I guess, right? Anyway, so let's go on here to explain 2. So now we're going to also use slopes to help us find missing vertices. Okay, so example 2 asks us to find the coordinates of the missing vertex in each parallelogram. So now we know we want this shape to be a parallelogram. Okay, we want this shape to be a parallelogram. And we're given 3 of the coordinates. So they already took the, I don't know, gave us the points they're graphed. Okay. And so we connect A to B and A to D. Right? A to B, A to D. And so we know that C is going to have to go somewhere up in here. Right? Somewhere up in here. How do we know where it's got to go? Or sorry, point C has got to go somewhere up in here. All right, so how can we know what to do? Well, DC is going to have to be parallel to what? Has to be parallel to AB. Or you can think of it as AD will have to be parallel to BC. Okay? So either way there, you can use whichever one you want. I think they choose to use AB to guide themselves here. So we'll just count our slopes here. From A to B, we have to go up 1, 2, 3, 4, 5, and left 1, 2, 3. Okay, you can see that right here. So B, from A to B, we have to go up 5, left 3. And then so from D, to get that same kind of parallel, segment, we're going to go up 5 and left 3 as well. And boom, there's C. Okay, so the coordinates of C are 2, 4. Okay. Wow, and a triangle ABCD, that should be the parallelogram symbol there. Okay, I don't know why I put a triangle there. Mistype, error. Okay. All right, let's try letter B. All right, PQRS, parallelogram. Again, that's a parallelogram symbol, so we're going to assume it's a parallelogram. PQRS with vertices -3, 0. Please make sure you plot accurately, right? That's going to really mess you up. Q, -2, -2, positive 4. And then R, 2, 2. Okay. It can get a little bit confusing here, so make sure you connect things that are supposed to connect, right? P, Q, R, S. So P to Q, Q to R, and then P and R will connect both to S. Okay, please don't forget to draw in your sides. It will be helpful. Okay, so let's see here. Let's go to, so Daniel, pick a point. Do you want to count from P or do you want to count from R?
Doesn't it say to count from R?
Okay, you want to count from R?
Sure.
Okay, so then from R, right, so R to S is going to have to be parallel to what part of our parallelogram here? To go from R to S, that segment is going to be parallel to what part of our parallelogram here?
QP.
QP, right. So from Q down to P, we're going to go down 4, left 1. So then from R down to S, we're going to go down 1, 2, 3, 4, and left 1. And there's where S has to be. Okay, so S has coordinates 1, -2. We did not have to count from R, though. We could have counted from P. Okay? If we chose to count from P, P to S would be parallel to QR here. And so again, you want to count down to right 4. So then from P to S would also be down to right 4, and that would get us to our point S there. Okay? There it is. Questions on any of that? Too easy? All right, that's what I like to hear. All right, then 7 and 8, go ahead and give those a try. All right, give 7 and 8 a try there. Oops. Okay. Let's go to Emma. Emma, were you able to come up with an answer for number 7? You got 2, 0? Okay. So I got something else, but maybe I made an error here. So let's see. I got 0, 4. Did I graph it wrong, though? Let me check. -3, -2, 0, 1, 1, -3, and that was...
Would it be 4, 0?
Oh my gosh, yeah, 4, 0. Goodness gracious. But yes, 4, 0 there. So, okay. Yeah. And what, Emily, what would you say your answer was? I'm sorry.
I said 2-0, but.
2, 0. Okay.
Oh,
Did you put M in the wrong spot? Yeah. Okay. There it is. Okay. Gotcha. So yep. Okay. Yes. Plotting those points, right? Even Mr. Wig can't read the coordinates sometimes. Okay. So anyway, there are your answers. Okay. And then there is letter D. Point D is at -3, -1. Okay. And my recommendation when you're figuring these out, make sure you also connect. Like J connects to K. K does not connect to M. Okay. J connects to K. J connects to M. All right, but K don't connect. Don't connect what doesn't connect here, right? J connects to K. K connects to L. L connects to M, and then M connects back to J. Okay, same thing here. D, E, F, G. D to E, E to F, F to G, G back to D. Okay. All righty. So there's that. All right. Questions on any of that? On Monday we'll talk about perpendicular lines. Okay, and perpendicular slopes, and then how we can use those slopes to help us show properties of other quadrilaterals, right? Okay, because we had other quadrilaterals that dealt with more, perpendicular stuff, rectangles, rhombuses, right, squares. So let me give you guys your assignment. Okay, you guys can start on that, and hopefully won't have any hope for the weekend if you get it all done here. All right. So starting on page 501, I'd like you to do numbers. 2 through 11, but you can skip numbers 5, 9, and 12. Oh, just 5 and 9. Sorry, skip numbers 5 and 9. Obviously, 12 is not in that range there. Okay, so you can skip numbers 5 and 9. And then I also want us to do number 19 and 24. Okay? And that's it. And of course, there's your 10 marks assignment as well, okay? Don't forget to work on your 10 marks assignment as well, if you haven't done that yet.